Let us look at our first case where we are going to see what happens when we put conductors of different shapes inside external electric fields. And we are going to derive 5 rules, and all those rules are always and always going to be obeyed. So what we are interested in is that we have a conductor. I'm drawing an arbitrary shape, and this conductor is put in a field which is externally created. So there are some charges which may be present, for example, around here, which creates an external electric field. And in that external electric field, I have introduced this conductor. The first question we want to answer is what would the total electric field inside the conductor be? Well, that external electric field which we have created, that would start to move electrons. So an electron from one atom would hop in here. That would leave a space open. Another electron would hop in. Another electron would hop in. This hopping process would happen. And electrons will start gathering at one side, leaving the other side vacant. And thus on the other side, I would start collecting positive charges. What would happen is that I would create an induced electric field, I induced. So this is an induced electric field due to E external. If I remove the external field, if I remove the charges which was creating that external field, conductor will go back to its original rest state and nothing exciting would happen. So this field inside the conductor is being induced by the external field, and that field is actually opposing the external field. It is going from the positive on the back side of the conductor to the negative on the front side. The back side is acting like a fan, the front side is acting like a vacuum. That induced field is flowing in this direction. The total field inside the conductor would be, at any point, would be the sum of the external field plus E induced. The electron which is sitting at an atom at a point here, that electron is going to see the total electric field I observe. How long will this process continue? Well, till this value E exists, the electron is feeling a force and the electron will move. When will this process stop? When E everywhere inside the conductor goes to 0. As electrons are collecting on the front surface, leaving more positive charges on the back surface, E induced is increasing, and this will keep on increasing till E induced becomes equal to E external, and thus E total electric field inside the conductor goes to 0. And once the total electric field inside goes to 0, electrons left in the atoms have no more forces acting on them, and this process would stop. So here comes in our first major rule. In equilibrium, total electric field E inside the conductor would be zero. In equilibrium, if I go and try to measure the field inside, that field has to be zero. This field includes the external field and the induced field you have created, which is induced by that external. But the sum of those has to be zero. Thus, the electric field inside the conductor has to be zero. That makes your first important rule. And at least for conductors without resistances, this rule would always be obeyed. You can never break this rule. Out of this rule comes your second rule. If your E inside the conductor is zero, and I go from a point A to a point B and calculate what your potential difference is, which is an integral of A to B E dot dl, but we have said electric field inside is zero. Thus, the potential difference inside is going to be zero too. Any point I go to, whether the point is internal as I have drawn, or the points are on the surfaces, or the points are, one point is on the surface or on the other surface, the potential difference is always going to be zero between any points. There is no potential difference created between different points in this ideal conductor. This is exactly what you're doing in ECE 140 also. You're assuming that the wires are perfect and there is no voltage drop which is created across a wire. So that makes my rule 2, which is conductors are equipotential. Every point on the conductor has the same potential. The potential may not be zero, but whatever is the potential at one point would be the same potential at another point too. That makes our second rule. And for perfect conductors, the second rule can also never be broken. Again, going back to what we have, the same rules we have discussed, we can derive our third rule. We have this external field hitting the conductor, which would start attracting electrons towards itself, leaving positive charges on the backside. So what you would end up getting is that on these surfaces there would be an induced charge on the surface. These electrons, and again, that goes back to the condition we had put on the ideal conductor, that the electrons can only move as far as the surface of the conductor is. So when I have this conductor, I apply an external electric field. The charges will start collecting on the surface, and on one surface, as I have drawn it, I would start collecting negative charges, and on the back surface where these charges have come from, I would create positive charges. And that's my third rule, that there are charges induced on the surface of the conductor. These charges of the total electric field would be related, and we would see that relation mathematically later on in the chapter, and that is called a boundary condition. However, we should be very clear that as soon as we put a conductor in an electric field, we would start inducing negative charges on one surface and positive charges on the back surface. What about what happens in the volume? We have said that there would be negative charges which are induced on that surface and positive charges induced on the surface. So we have some rho s2 and rho s1 created here. But would there be any induced charges inside the volume? Can that exist? Again, remember, the first rule we derived was that the electric field inside the conductor is zero. So what we can do to see what would happen is simply use a friendly Gauss law, make a closed surface, and I'm drawing an arbitrary closed surface there. And on this surface, if we calculate that flux should be equal to Q net by epsilon naught. But we have already concluded that the electric field inside the conductor is zero. So this integral is simply an integral of zero. You are summing these zeros up many, many times, and all you are getting is Q net is equal to zero. There cannot be any volume charge. That is your rule 4. There is no volume charge inside conductor. Now hopefully you see some important applications of Gauss law. We would not have been able to come to this conclusion without Gauss law. Because Gauss law we have already concluded is universally true, Gauss law has to be obeyed. Electric field inside the conductor is zero. That guarantees me that the charge in the volume of the conductor has to be zero too. All the charge which would be induced would be induced only on the surfaces. So let's summarize the rules we have created so far. We have said we take a conductor, put it in an external electric field, we will start inducing charges on the surface such that electrons start collecting towards the electric field, leaving positive charges on the back end. Electric field inside goes to zero. Delta V in any 2 points on the conductor goes to zero, so the conductor becomes equipotential. However, the Q total is still zero. All we have done is taken these electrons from some other place and left positive charges in another place. We have not added electrons, we have not added positive charges. All we have done is whatever charges were present in the conductor, because the electrons were so weakly bounded to the atom, we have redistributed that charge. We have taken charge from one part of the conductor and moved it to another surface. That's what we have ended up doing. These are the first four rules. The next rule is based on this very simple idea that if I have a conductor, I have external field which is created. I have created electrons on one surface and left positive charges on the other surface. So now I have started creating an induced electric field outside too. So there is an induced electric field, and the total electric field which I would have would be E external plus E induced. That would give me the total electric field on any conductor. Let's see what happens. We've already decided that the total electric field inside the conductor is zero. But what I'm interested now in is seeing what would happen if I go right at the boundary and look at what is the total E field just outside that boundary of the conductor. And the rule is this, that if, I'm just blowing that boundary up. So I'm just going to the boundary. There is negative charges which have collected here. If there is a tangential component of that total electric field, E, just outside of the surface in air for the time being, just outside that conductor, if there is a tangential component of the electric field, then what would happen? These electrons will start moving downwards. So the surface would basically not have that original uniform electrons I have. There would be more electrons which would start gathering here, less electrons on the top. If this was existing, which would create a field which is opposite to the original red field I have. And this motion would happen till this cancels out. So rule 5 is there is no tangential field or electric field at the boundary of the conductor. This is at, or if you want to be slightly more clear, you can say just outside. If I just go outside the boundary, there cannot be a field which is parallel to the conductor boundary. That is not possible. If there is a field which is present there, the electrons will start moving, creating a field in the opposite direction to cancel that field out. How long will that happen? Till that field is cancelled out. So when I go in equilibrium, that parallel component of the field, or the tangential component, we call it the tangential component, it's tangent to the boundary, that tangential component of the field will have to be 0. What that means is that if I have this conductor, the electrons are going to adjust in such a way that the total field will bend and hit the conductor always 90 degrees to it. Wherever I go, this would hit 90 degrees to the conductor. Now the total field outside, think of you had these fans which started creating your E external. Part of these E external hairs would be attracted by the vacuum you have created, and thus the total field, which would be E external plus E induced, that would be created in such a way that everywhere I go on the boundary, the field will have to be incident on that boundary at 90 degrees. There is absolutely no way you can break this rule too. There is no tangential component. Tangential means parallel. There is no tangential component of E at air conductor boundary. Field will have to hit the conductor at 90 degrees to the surface. And the technical word we use for this 90 degrees is normal. That the field would have to hit the conductor at normal incidence means that the field will have to hit the surface at 90 degrees.